All right, it's time to begin, so we'll go ahead and start. Today we're going to be getting into, some of this should look familiar. The idea of a Venn diagram is something you've probably seen before, representing sets. We're getting into sets because many of the things that we look at in computers, we're actually looking at sets of things that we're able to represent within the ones and zeros of the computer. So, there's actually only a set of integers that we can represent. We can't represent every single integer physically inside the computer. So one thing before we get into everything else, and we'll talk about some of the other things here, or we've got a little bit of time today. Before we get into anything else, starting on Thursday, so day after tomorrow, we'll be in room 318 rather than in here, so that the monitors and computers that you're sitting in front of, which I don't think anyone is actually using, won't be there anymore. So we'll be in a room where you'll be able to plug in your laptop and get things going. I think you can plug some of them in here. But we'll be switching with the class that we switched with at the beginning of the semester because they needed more room. So, all right, our topics for today. As usual, we're going to do a review. We finished last week. We were talking about predicates and quantifiers. We began the week with a little bit of Boolean algebra. We talked about some prologue and other stuff like that. But predicates and quantifiers were the way we ended up the week and finished with, that off. We'll start talking about sets, and we'll look at the idea of subsets and the size of sets, the Cartesian product of sets, and set quantifiers. And then we'll delve into set operations, some of the terminology that we have. And set operations are things that you've probably seen before as well. Things like union, when you combine two sets, intersection, what elements do they share, that kind of thing. The set difference and symmetric difference. We'll also look at computer representation of sets, and we'll be basing our third program off that idea. And I'll start talking about the third program today. It tends to be one that people struggle with if they don't understand that no matter what you do on a computer, you're dealing with ones and zeros. If you understand that, then this is not a big leap. If you think of it in terms of, the computer can represent sets in Java or C++, or I can have vectors and arrays and other stuff like that, the idea of using an integer to represent a set is going to be a little painful. And we'll talk about that as we get through here. And then at the final part of the class, we'll start looking at using a bit string, and that's what we're going to talk about. The third program is called Manipulating Bits. It's the first part of the title. So that's what we're going to be doing, is looking at bitwise operations on integers in order to represent sets. Yep. And then we'll talk about what a bit string is as well. So with our review, propositions, and we're going to go all the way back. Day one. A proposition is, or propositions are, something that is true or false. A true-false statement. A statement that is either true or false. So we can't have any variables. It can't be an opinion. It can't be a command. It can't. Wrong arrow. New keyboard. Wrong arrow. It can't be a command, it can't be a question, that sort of thing. We then added the idea of predicates, and predicates are propositions that have variables. So that's really the only difference. A predicate is something that talks about true, false, with regard to the elements of some set. For the set of all the people in this class, no one has AB positive blood. That'll be either true or false. I can only speak to my own blood type. I have no idea about you guys. I know AB positive is rare, so actually I guess AB negative would be more rare, but our predicates are talking about variables, and those variables come from a set. And that's really the key idea there. They have to be defined over a set, And the predicate itself is a statement about elements of the set. So it will be, when X is an element of the set, X has a B negative blood. And that would be true or false for each individual. And it's not until we actually add quantifiers that we end up getting something over the entire set. So we have to have a value from the set for our predicate, and then from there we talk about quantifiers to look at how the properties of that predicate vary over the set of things that are that we're talking about. People on the planet, cars in the parking lot, whatever the set happens to be. We talk about buildings on the campus of Weber State. All buildings on the campus of Weber State are at least 3 stories tall. It'll be true or false, I don't know. Or there are buildings on the campus of Weber State that are at least 3 stories tall. Once again, it would be true or false, depending on the entire set of buildings. And then there exists only one building on the campus of Weber State that is 3 stories tall. And that may or may not be true. So we have our 3 quantifiers. The universal quantifier, we use the words for all, for every. We're simply saying that it doesn't matter which thing you're talking about, the predicate itself is true for every one of the things in our set. So if we're talking about the people in this classroom, for everybody in this classroom, each of us has a W number. That would be true. You all have W numbers or you couldn't register, and I have a W number because I'm an employee of the university. So everybody in this classroom has a W number, and that would be a true universal quantifier. For everyone in this class, everyone is paid by by Weber State University. You guys get paid by the university? No, you probably pay quite a bit to come to school. So that's the difference, is the quantifier itself doesn't change whether it's true or false. It simply says that the truth or falsehood is dependent upon the predicate applied to every element of the set. Same thing for our existential. Does any exist? Are there any? Would be another way to look at this. There exists. So, this is definitely, is this going to be true or false? There exists at X, an element of the students in this class, such that X will receive an A. True or false? Well, ultimately, it will be true or false. So, we don't know yet, I guess would be the thing. So we're predicting the future. I strongly predict that there will be at least one. So there exists a student in the class that will receive an A. And then there's the uniqueness quantifier, which says that not only does one exist, but that is a unique value. There's an element of the set of integers such that the reciprocal of that element is undefined. Everybody remember what the reciprocal is? 1 divided by. So are there any integers such that 1 divided by the integer is not defined? Are there any? Yeah. Are there more than 1? Like, are there 2? What's 1 over infinity? Well, infinity is not specifically an integer. What's 1 over 10 to the 1,000th? Or 10 to the 1,000th? It's a really small number, but it's a number. It's defined. We have a way of actually doing it. What's 1 over 0? Undefined. Are there any other integers such that 1 divided by that integer is undefined? No. So 0 is a unique element of the set of integers such that it is unique in that its reciprocal is undefined. We can also say This may or may not be true. There exists uniquely one person in this course who was born in Illinois. Anybody in here born in Illinois? Yeah. Pardon me?
Were you?
Yes, I was. So that's why it still may or may not be true. Maybe I was born in Montana. No, I wasn't. I was actually born in Illinois. But that, unless somebody online was born in Illinois, then this would be a true one. If somebody online was born in Illinois, it would not be true. But that's just like everything else. We're simply talking about, well, it's going to be true or false. We can still make the statement and then determine the truth or falsehood of it. And I'll just remind you, all of these things are operations that work on symbols. And that's really all. We're just trying to determine. Don't put any emotional value in the truth or falsehood of anything you see. There's nothing emotional about it. It should be either true or false. And that's really all we're interested in. And with the quantifier, the predicate will be either true or false. Without the quantifier, it's true or false only when without the quantifier, the predicate would be P of X is the predicate that X was born in Illinois. Is it true or false? It's not talking about whether there exists anything or anything else. When do predicates have a truth or false value? A true or false value? I probably should have done this before we did the quantifiers. Is on the previous slide.
Doesn't it when the variable only have the whatever the variable is?
Yeah, we have to have the value for the variable to be able to determine, but that's really all the only requirement there if I only have the predicate without the quantifier. But once I provide the quantifier, I can say the predicate itself is either true or false without talking about the specific values that make it either true or false. Alrighty, speeding along here. In prologue, everything is a predicate or a proposition. Propositions, things that are true or false. Well, we really don't state any of the false things. When you write a prologue program, what's the very first thing that you put in there? Facts. Facts are things that by definition are true in the program that you're writing. You're defining those things as true. That means that they are propositions that just happen to be true. You define everything that on its own, without a variable value in it, is true. And then you come up with a rule. A rule is a predicate because it has variables in it. So what prologue does is it uses the facts that are provided and the rules that show how to combine them to determine the truth or falsehood of those expressions. So our facts are our propositions, our rules or predicates are our rules, and so here's an example. The comma here indicates what? An and. Yeah. It's an operation within the prologue language. It's treated like an and. So the thing on the left, something one will be true when another thing is true and another thing two is true. So when those two things are true, the thing on the left of the colon minus will be true. Yep, wrong arrow. The keyboard's different on this. So I had to go out and get a numeric keypad to do some things. But what this is saying is that if another thing one and another thing two, or that another thing one and another thing true imply something. That is the equivalent expression of this. That colon minus is simply the implication operator or the conditional operator backwards. So that is all that anything in prologue is. It's either a proposition or a predicate that uses conditional statements. Comma is an and, semicolon is an or, and a colon minus is a backwards arrow. Oh yeah, and the reason why you can't do this, stops stops plus one, is because stops is stops plus one would always be I can't do an S. It's false. It's always a false statement. That's why we had to have that other variable in there for the recursive call. Because the only way that we can do this is to have a name here that's different than this one, and that gives us the opportunity to have it be true. So it'll try and plug in values that will make it true. So our recursion stops. Yeah. There is no value of stops where stops plus one is equal to true. Stops is equal to stops plus one, which is really what that statement is saying. So. Okay. Oh, I went the wrong way. Hit the wrong arrow again. So the result is, if we had that in our program, everything would be false. Once again, Prolog is a logic language. Everything is either a proposition or a predicate, and we have to understand that to understand how it's doing what it's doing. Things like a right are defined because they don't have a variable value in them, are treated as always true, and that's why we can put them into a predicate and we can get the cities printed out or something like that. That operation of writing something is always treated as true, and it's only when the other things are false that we don't get it written. So let's talk about sets. Everybody's favorite Venn diagram on the right showing the intersection of three different sets. A set is simply a collection of unique things. Unique is important because when we look at a set, we don't have any duplicate elements. That's one of the things that is sometimes hard to understand. If, for example, you had a set of marbles and you had two agates, an agate's a clear one with kind of there's something inside it to make it look like something else. If I remember right, I haven't played with marbles in a long, long time. But the idea is that no two marbles could be identical. There would have to be some small thing that makes them different. It's like Oriental rugs. If you were to go to somewhere in Asia, I have some Kashmiri rugs that I got when I was in Saudi Arabia, and I was talking to the guy who was selling them, and he said, yeah, they're always not perfect, first of all because they're made by hand, but even if the pattern itself is implemented perfectly, there's always a small flaw that's put in there because you don't want to tempt fate that everything's perfect. You're not trying to get the gods or God angry with you because you did something perfect. So that would mean that every one of the rugs, even if I had a pile of rugs this tall, all of them made in same pattern, same wool and silk and stuff and colors and everything else, each one of them would be different. And that's the idea of uniqueness there. For the most part, we don't treat things that way. For example, if I have a set of cars and they're all black Tesla Model S, they're plaids with the same features and everything else, we'd say that's a set of cars. For the sake of mathematical correctness, we would say, no, you either have one Tesla or you have something else. All of them are called elements or members of the set. Unique means that no two are exactly the same. From a mathematical perspective, we can say that, and we can kind of think of that in terms of physical things by being able to say, oh, well, physically, you're using different atoms than somebody else, or your Model T, your Model T, your Tesla is different than my Tesla because you've got different carbon fiber in it than I have in mine. We have symbols here. We have a small epsilon. This is the thing that means whether or not something is an element. We usually write the set as a capital letter, and then the elements of the set as small letters when we're talking about them symbolically like this. So we would say that A is an element of set A, or A is not an element of set A. And that's simply the epsilon with a line through it. Keep hitting the wrong arrow. We have some special sets. You've seen these already. We talked about them a little bit with our predicate expressions. N, this is an overstrike N. It's got the two vertical lines. It basically means that I've got the set of natural numbers starting with 0. We oftentimes will call these counting numbers as well. There are textbooks where natural numbers are defined as 1 and up, so which would be the same as positive integers. But for our text and our purposes this semester, we'll treat it starting at 0. We have the set of integers, an infinite set that goes from negative infinity to positive infinity, where there is no fractional part for any of them. We also have a portion of that we can indicate by having a plus sign to indicate that we're only taking the positive values from the set. Normally we're not going to write a z minus. You could, and I think most mathematicians would be able to understand that. We're not mathematicians, we don't care. So that's a joke, by the way. But I don't believe I have anything, and I don't believe the textbook has anything that uses that. By the way, just as a reminder, in the textbook, a lot of the problems that are in the textbook form the basis for some of the questions that I have on exams. So if you go through the problem sets in the chapters, it might make the, if I remember right, all the odd questions have answers in the back of the book. So you can practice some of the things without taking the quiz, and then you can get a high quiz score and be prepared for the exam. Q is the set of rational numbers, a fraction with an integer numerator and an integer denominator, as opposed to the irrational, which are like a lot of people. Wrong kind of rational. R is the set of real numbers, where R plus is the set of positive real numbers again. Once again, all of these are overstrike images, and you will see them with overstrikes probably 90% of the time, something like that. And then finally, we've got C, the set of complex numbers. It has a real part and an imaginary part, and that gives us the ability to do things like get the square root of -1. So a few more ideas. We have things like set builder notation, which basically gives us the ability to define a set by showing how we can construct the elements. So we get the properties, and we've done that several different ways. For example, we could have let A be the set of X, where X is an element of the set of positive integers, such that, that's what the vertical line means here. It does vertical symbols in math often have multiple meanings. And here the vertical line simply means we read that or we say it as such that. So we're separating the overarching set from how we build elements of the set we're defining. So we say X comes from the set of positive integers, and then on the other, and then we define how we build that set and say that X is prime and X is less than 100. We could say X is less than or equal to 100 because 100 is not prime. So it wouldn't make any difference if we included that or just an aside there. I happened to notice that. And, squirrel. Oh wait, no. Shiny thing. A set can contain other sets as elements. This is another thing that causes people problems occasionally. Here, for example, let's say that we have the set n, z, q, and r. The set of the set that contains the set of integers, the set of the set of natural numbers, the set of integers, the set of rational numbers, and the set of real numbers. So we have 4 elements, 4 things in this set. It just happens that each one of those, how many things are there in the set of natural numbers? Natural numbers are the numbers starting at 0, counting numbers, and going to positive infinity. So how many things are in it? Infinity. We have the set of integers. How big is the set of integers? Man, tough room. Must have been a long weekend. Or you were up late last night studying, reading your, well, actually, if you were reading the textbook, you probably fell asleep. So it can be a little dry. Quotients, I've got an integer on the top and an integer on the bottom there. Both of those are infinite sets, but countably infinite, so I've got a countably infinite number of rational numbers. And then I've got real numbers, another infinite set. That one's bigger than the set of integers. Yes, there are different sizes of infinity, but this set, even though each element of it is infinite in size, the size of this set is 4. There are only 4 things in it. Each one of them just happens to be a set. And this is the aside. I wanted to throw this at you because sometimes you may just see them as capital letters. Usually they're going to be bold or some other way, but overstrike is how I normally will present them, and you may see them other ways. We say 2 sets are equal only if they contain exactly the same elements. So, if you have 2 neighbors and they both have, 2 kids, a dog, 2 cats, and a Chevy Tahoe, hopefully they are not sharing them. So each one of them would be unique. So they would not be the same elements at that point. But if they are sharing them, then yeah, they have exactly the same elements. Here's an example. Let A be the set 0, 1, 2, 3, 4, etc. The ... here indicates that I'm continuing a pattern, so I don't have to explicitly list all the elements of this particular set. Because the numbers, the integer values that I've listed there are the same as we have in the set of natural numbers, then we can say that set A is equal to the set of natural numbers. If we let B be the set containing the set of natural numbers, then we'd say that B is not equal to the set of natural numbers. Why? Because it is a set containing a set. Just like the set up here in the example with the 4 sets of natural integers, rational and real numbers, that's a set with 4 elements. Here I have another set, but it's only got one thing in it, a set that contains the natural numbers 0 through whatever. And that means that they're not the same. B has only one set as an element, and N has an infinite number of integers as elements. So a set inside a set is not the same as the set itself. And we will see that when we talk about some other things coming up. We do have one special set. We call it the empty set. It's the set with nothing in it. Oftentimes it's written here with a phi. That's a 0 with a line through it is what a phi looks like. Phi or phi. You might hear, actually I guess it's phi. Phi, phi, fo, fum. So PHI, because the Greeks spell things weird. That's a joke, by the way. So we also call it the null set, and we may write it also as a set of empty brackets. So we usually write our sets with curly braces, and then we list the elements of the set. So null set, empty set, oftentimes will be the same thing, and we have some special cases for those. We use Venn diagrams to represent a set. We have an example there. What is a Venn diagram? What's the box? It's like a frame on a picture.
They just contain three main sets in there.
Yeah, but it too represents something. The box represents something for us.
Is the box a set, and then A, B, and C would be the elements in a set?
Yeah, they're not really elements, they're more subsets. They're sets that contain things from a universe. Everything that we put into a set comes from somewhere. And we call that somewhere a universe. And we can define the universe in different ways. We can define the universe as the people in the world, the automobiles in the parking lot, every atom in the universe. And at that point, we can then say, well, this set is the set of atoms contained within Bob. See Bob here? See all the atoms that are in Bob? And that would be, Bob would be kind of a subset of the entire set of atoms from the universe. Same thing with automobiles in the parking lot. A might be those automobiles that are driven by students. And B might be those automobiles driven by staff. Well, there are some staff people that take classes. So they are both students and staff. And then C, I don't know how to define C in that particular case. But each thing here is a rectangle where we have a set of objects where we're drawing things from to create the other sets. The sets that we're talking about. A lot of times the box will be left out, but we're still usually looking at some universal set, like the set of numbers. You know, for most math problems, that's what you're talking about, the set of numbers. Well, is that set the set of all numbers? Is it the set of integers? Is it the set of real numbers? Is it the set of, so we start taking that set of all possible numbers, and then if you look at the cover slide, that was what the image on the left was, the Venn diagram with complex numbers, real numbers, rational and irrational numbers, and and then it went down from there to integers and stuff. They used whole numbers, so I have to look up whole number to make sure that I have the definition down consistent with what they did. Inside our universe, we identify the sets by some kind of line, enclosed figure of some sort, a diagram, usually a circle. But I've got a nice picture on the next slide where it's not a circle. It's actually kind of neat. I like the one on the other one. There are instances where I might have, for example, this one lists, it's not clear whether it's listing specific elements, whether A is a specific element, or it's talking about some region or subset of set A, or of this top circle. So A, D, G, E are all inside one set, but is A a specific element or is it something else? It's not clear from the diagram. You would assume that these are specific elements, but they could also be identifying regions of it. And you can list these either with or without a dot. If there was a dot there, then I would definitely say, well, A is an element. The dot is telling me that if I were to look at a picture of this set, it would be right here in that dot. The dot really doesn't give you a location, but it tells you, it would give us more information saying that A is an element because there would be a dot next to it that would be labeled. So let's take a look at a more interesting Venn diagram than that one. This one happens to be from Creative Commons. It's looking at food, high protein foods, low fat. I forget what else is in here. We've got vegetarian foods. We have high fiber foods. We don't have any high fat foods unless they're not in the set of low fat. I guess that means that they're high fat. But what we see is that while normally we draw circles, you don't have to draw circles. You can draw any shape you want if you're listing all the elements in your universe and trying to determine what thing is going in what sets and what overlap there might be. For example, let's say that I want low fat, high fiber, and low protein. Then I'm looking at collard greens. Actually, they're not too bad if they're cooked properly. If you're from the South, they're kind of tasty. If you're a Yankee like me, then you have no idea how to cook collard greens. But, I've lived in the South, and they were actually pretty good. And then, of course, everybody's favorite, potato chips. Obviously, not high protein, not low fat, not high fiber, but boy, they're really good with dip. How can you beat that? Jello salad, it's not high fat. I wouldn't say I would actually say, well, no, Jello salad has like whipped cream and other stuff mixed with marshmallow, so high carbohydrate content, high fat content, but also tasty. Fruit and Jello all mixed together. I've never had duck confit. I couldn't even tell you what that is, but this is one of those things that it kind of clearly demonstrates that there are a lot of different ways that we can draw the relationship between sets, and we shouldn't get wrapped around the axle about it. And this obviously doesn't represent every possible food out there. The sets are outlined in different colors, red, blue, yellow, and green. Our universe is defined by a black box around the outside, and we've even got a name for it. So the name is in the same color as the line that it says. So all foods fall into one of these categories or in none of them. I've got two that don't fall in any of the subsets that are defined here. So our Venn diagram shows when two things share elements, when one is completely inside another one. All of those kinds of things are things that we can represent with a Venn diagram. As an example, if I wanted all the things that were non-vegetarian, high fiber, non-vegetarian, high protein, then I've got this thing, which is a subset of both the low fat and the high protein things within our sets here. So see, I've solved my tablet problem here. I can write all over the top of it now. So, always fun. So we can say that this is a complete subset of the set of high protein as well as a complete subset of the set of low fat. It just happens to be the entire intersection of those two things. And then if we were to break that down a little more, we could look at, let's see, the terrestrial non-vegetarian proteins that are high protein and low fat, and that would give us those two, which would be a subset of something that is, they're terrestrial. Chickens and beef for some reason just don't tell me that they're aquatic, whereas tuna kind of swims around a little bit. So that's the kind of thing that we can represent with our Venn diagrams. So let's look a little bit more at subsets and supersets. Is the Superman symbol, I got this from Creative Commons, so I'm assuming that it's not trademarked. Otherwise, they would have shut down the Creative Commons part on it. But it didn't occur to me that maybe it would be. Anyway, if I have two sets, if all the elements of one are in the other, then we call it a subset. And we use a special symbol for that. It's like the less than or equal to sign, except rather than being straight lines or like a less than. It's a curved thing to indicate that it's a set operation as opposed to a numeric operation. We can also say in this case that B is a superset, and all we have to do is change the direction of that symbol, and it tells us the first thing is a superset, or it's bigger or equal to the other one. And the equal to part is indicated by the line underneath. If we have an instance where A is a subset of B and B is a subset of A, then the only thing that can make that happen is when this line that says that they potentially have the same elements is true. So in that case, they would have exactly the same sets. Neither contains more elements than the other one. If, however, we had a case where A was a subset of B and B was not a subset of A, then we know that there are some things in B that are not in A. And what we would then say is that B is a superset of A, or A is a proper subset. And by proper, when we say proper, we use the symbol, the cup, the sideways cup, or whatever you want to call it, the subset symbol without a line underneath it, to indicate this is, not only is this a subset, it is a proper subset in that there are things in the thing on the right that are not in the thing on the left here. So if we take the little equal sign off, then that changes the meaning a little bit. Just like it would with less than or greater than. There we go. Another thing that we can do is we can count. In fact, we'll be doing counting a lot this semester. Later on, we're going to be counting things to determine the probability of things. We'll be counting things and using formulas to do it because they're big things and it'd be hard to count a certain size of things. But here, we're talking about the size of a set. The size of a set is the number of elements that the set contains, and it's called the cardinality of the set. For example, with the empty set, what's the cardinality of the empty set? 0. It doesn't contain anything. The cardinality of the universe? Infinite. So, infinite number of things. Our cardinality is written. It looks similar to an absolute value. So in this case, you'd have to be told, if A is a set, what is A with the 2 lines on the outside there? And you say, I don't know. You haven't told me what the number is. In which case you would have missed that A was a set, and we're talking about how many elements A has in it. We can have 0 elements. Every other set has at least 1 element. That does have a consequence, which I believe I have in the next bullet, but I don't see my next bullet here yet. Okay. The power set is a set of all the subsets. In other words, if I wanted to list all the possible things that, how can I group people in this room into a set? Yeah, we're in 2130. But what if I just wanted to take, let's see, 3, 6, 8 of us. There are 8 of us in the room. What if I wanted to see how we could make a set of people from the 8 people in this room? How would I do that?
Get characteristics from everybody, and then you could pick any of those characteristics and see which one it applies to everyone, or who.
I could do it that way, or I could just randomly pick. We don't have to have anything specific to say that something's in a set. We could have a set, for example, that contains aardvarks, Ferraris, and PS5 consoles, or a PS5 console. Not any specific one of any. It only has one because it's a set, so it would have 1 aardvark, 1 Ferrari, and 1 PS5 console. What common characteristic do they have? Nothing really. One's an electronic device, one's an automobile, which makes it mechanical and electronic, and one of them's a living thing, or potentially dead if it's been running on the side of the road and decided to cross at the wrong time. But the idea is that a set can contain anything. They don't have to have a relationship to each other. So we just happen to have 8 people in here, but I can make a set by almost any, but by fiat. I could just say, okay, you and I are in a set. No real anything there. So how many sets can I have? I can have the empty set. Each of us could be in a set by ourselves. There are 8 of us in the room. That means that there would be 8 subsets. We would be subsets. As we're talking about, how do I build a power set? I could then say, okay, well, I also have sets that could contain 2 people. So it'd be you and me, 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 and you and me. So there'd be 7 sets with me. There'd be 6 more with you, 5 more with you, 4 more with you. And we'd go through that way to get the number of 2-person sets. Then we could go to 3. And so we just keep doing that until we finally listed every possible subset. 8 is a big number. We'll do a smaller one here. For example, let B be the set of the set containing the set of natural numbers. Then the power set is, well, what's the subset of B? It's the set containing the set of natural numbers, or the set that does not contain anything from the set, which would be the empty set or the set containing the set of natural numbers. Every set is a subset of itself, by the way. So the empty set is a subset of every set, and every set is its own subset. This one's more interesting. The set 1, 2, 3 contains the empty set. Each individual digit, each digit paired with 1 more digit, each digit paired with 2 other digits, but since I've only got 3 things, there's only one of those. One key thing when it comes to sets is the set 1, 2, 3 equal to the set 3, 2, 1. What is the property that makes a set? It is a collection of, begins with U, unique items. Order is not important. Doesn't matter what order things are in a set. When I list them, because I'm writing them down, I have to put them in some order. I can't just say, yeah, all the elements are here, and then not write anything. So I have to put them down in some particular order. But the order does not say what things are in the set. All that's important is that it's in or it's not in. You know, you're in the in group or you're not in the in group at school. I was never in the in group. I was in the band group. I was in my freshman year, I was in the track group. And then my senior year, I was in the nerd group too. The band group and the nerd group, because I was in I was taking calculus and well, anyway. So the order is not important though. That's the key thing here, is that the order is not important. A set has an element in it or doesn't have an element in it. It doesn't matter if it's the first element or the last element or the middle element in a list of things. Wrong arrow one more time. So we also have this idea of a Cartesian product. You've probably done this before. The term that you probably used before in algebra was a cross product. If I have 2 sets, I can make a cross product. What that means is I take one element from the first set, and then I have it listed with every single element of the second set. Then I take the next element of the first set, and I have every element of the second set listed with that. The thing with a cross product is, here, there is an implied order. If I have A cross product with B, that means everything that I list will have the element of A listed first and the element of B listed second. We'll see that in just a second here. Even if I don't have it on the slide, we'll do one. All right. It is a set of ordered pairs where the first one comes from the first set, the second one comes from the second set. Actually, I do have some examples here. So here, if I have A is equal to 1, 2, 3, B is equal to X, Y, Z, then my cross product is 1 listed with everything from B, 2 listed with everything from B, and 3 listed with everything from B. Is X2 an element of the cross product? No, it's not, because X is not an element of A, and 2 is not an element of B. So that's the only requirement, is that the first thing in this list has to come from this set, and the second one has to come from this other set. And because it's a set, I can only use them one time with each other. Yes?
So if it were B times A, then would X2 be the element in the set?
Yes, it would. If I have B cross A, that would equal the set X comma 1, X comma 2, X comma 3, Y comma 1. Oh, no, it's not a curly brace. I'm not done yet. Y comma 2. My hand does get a little heavy on the screen. It recognizes touch. That's the only bad thing about it. You can reduce its sensitivity, but not completely get rid of it. I'll make my curly brace a little nicer at the beginning here. So B cross A would have every element here flipped. And I can list them in this order, where I'd have X1, Y1, Z1, X2, Y2, Z2, and X3, Y3, Z3. The order is not important. The only thing is that I have to get all of them. So usually what we do is we'll list one element with all the elements from the second set first. That way, that also gives us the ability to kind of list it as a matrix. Where I might have set A as my indices here, set B as my indices here, and then this would be element A2, A2, B2, whatever's second in my list when I list out my sets. But that's kind of the concept that we're looking at. We're filling in a set. So if I have, in this case, I've got two sets of 3 elements. How many elements am I going to have in the cross product or the Cartesian product? One set has 3 elements, the other one has 3. You can count them here. There's 9. What if I had one that had 5 elements and the other one had 10? 50. Or if I had 2 and 300? 600. So the number of elements in the in that Cartesian product is going to be the size of one set times the size of the second set. The order comes only from the first element being in the first set and the second from the second set. So that's why we have the term ordered pairs. It doesn't mean that, one's always got to come before 2, because the elements of a single set are not ordered. So I could just as easily have zebras, giraffes, impalas, and lions as one set, and kumquats, kiwis, watermelon and cantaloupe is the second one. And I can pair them that way. You know, does a giraffe come before an impala? Well, if they're alphabetically listed, but if they're listed by sight, the giraffe would, or well, okay, or by height, or inverse order by height, then the impala would come first. So. Okay, and we can have a Cartesian product of multiple sets. All that means is, and these will come back later on when we talk about languages and we talk about machines. Virtual machines are things that we define as it being a conceptual machine of computation. We'll be talking about a tuple, and a tuple is nothing but one thing. The first element comes from one set, the second element comes from another set, and we define it that way. So it's a Cartesian product of higher order sets. In general, I could have any number of sets, A1 through AN, and my result is an n tuple where the first element comes from the first set, the second element comes from the second set, the third element comes from the third set, and so on. And then I'd just list them, and I'd have A1 with every possible combination of the other ones. This gets big very quickly. So if I had another 3-element set, let's say I have 1, 2, 3, X, Y, Z, and apple, banana, pear. How many elements would be in the Cartesian product? Pardon me?
Would it be 27?
Yep, 27. The size of one set times the size of the next set times the size of the other set. So as my sets grow, the more things that I throw in there, the bigger the Cartesian product is. So we tend to write them down more with just an indication that I've got sets A1 through AN, and then I list the elements. Well, it just means that the first one's from the first set and the second one's from the second set, and we let it go that way. We don't try and list them out. 27 things written down is painful, especially in a classroom. Ordered pairs by definition would be a 2-tuple. 2 happens to be the number of sets, and an n-tuple is n things. And not too much else here. Just as an aside, databases, especially relational databases, are typically defined as being a subset of the Cartesian products. So if I have a set of addresses, a set of people, a set of phone numbers, then each individual would be, and their address and phone number would be a tuple, one item from that combination. And if they happen to live in 2 places, then they might have 2 addresses and 2 phone numbers associated with themselves as opposed to 1. But it would still be, the person would still be the same, it's just that the other 2 elements might be different. Databases will operate in that way, where we might have names, social security numbers, addresses, other things like that, and then we can go through the database and find out, well, there are 4 people living at this house, these are their social security numbers, these are their names, their aliases are over here, we can tell because their social security numbers are the same, like a maiden name versus their married name. Those are the kinds of things that we can do with the database, and it's really just, we've got these sets of data that we're collecting, and we have ways of looking at it, and the elements of the database are defined as a subset of that Cartesian product. So we could have name, phone, address, social security number, everything else. When it comes to sets, we can use quantifiers. Our universe in and of itself is a set, so it's the set that our values come from. And using our special sets, we've seen this before. For every x element of the set of z, what's z? The last element of the alphabet? Integers. Yeah, here it happens to be integers. We would say that x cubed is greater than or equal to x. Once we say that, we now have a predicate a quantified predicate has a value. This one happens to be true, false. Yes, true or false. It would be false because what's negative 3 squared? Negative 8. So it's smaller. You really have to be careful with the mathematics on these, and that's kind of the thing. So as we know, the upside down is the universal quantifier, z is the set of integers. Is this true? Nope. No, it's not. So just be careful as you're going through. It's always, we're taught so early on that integers are positive that we have a lot of people get a mental block saying, oh, yeah, if I put 2 in there, it works. Or if I put 10 in there, it works. And then a negative number can set them up for failure. How are we doing? Okay. So union is one of the operations that we have on sets. This is a cup. It's a big U. You can tell it's not a U because it doesn't have the little dangly thing off the side. But that's the operator, and basically it defines a set as being a set that contains elements that anything that is in one or the other or both. So if I had this set, A is equal to 1, 2, 3, B is equal to A, B, C, then the union would be a Michael Jackson song, A, B, C, easy as 1, 2, 3, whatever. The intersection is only those elements that are in both, the components or elements of both of the sets. We invert the symbol, so now it's an upside down cup. And this would be if I have 1, 2, 3, and 2, 3, 4, 5, then the intersection is only the things that they share, those items that they share. And we consider them unique in that if they're in both sets, it's the same thing. 1, 2, 3, ABC, the intersection is the empty set. There is always an intersection, there is always a union. It may be empty, it may have things in it. The difference is those elements that are in one and not in the other. The difference operator is written with a minus sign. Here, for example, I have 1, 2, 3 and 2, 3, 4, 5. This would be the things in A that are not in B. And in this case, it just happens to be the only single element, 1. So when we do this in our program, what we'll be doing is we'll be cheating a little bit, and we'll say that A intersect, or AND, is an intersect operation with the complement of B, or A intersect the complement of B. All the things in the universe that are not in B, and we'll do an A intersect with that. So that's how we'll do our operation as well. We do have one more that we work with. It's called the symmetric difference. In this case, it's the things that are in one or the other, but not both. It's kind of like, actually uses the same operator as So we have that same operator, XOR operator, and we're going to use that to our advantage when we actually program it. Here, for example, 1, 2, 3, 2, 3, 4, 5 again. 1 is A minus B. 4, 5 is B minus A, so we just combine them. The things that are in one and not in the other. But we could do something more complex, like the union minus the intersection would be the same thing, and that would be way too complicated. And then our complement is the set of all things that are in the universe that are not in a particular set. So here, if the universe is 1, 2, 3, 4, 5, and A is 1, 2, 3, then the complement of A would be 2 and 4. Now, odd numbers, even numbers, kind of thing here. They're complements of each other. Some of the things that we do, common way to represent them, and this is the way that we're going to be using in our program, is called bit strings. Another thing that you'll find in many languages is a predefined type for sets. So you might have, I know C++ has something called a set, and I don't remember how it's implemented. I believe Java has something as well. When you write program 3, you will not be able to use those unless you only want half the credit. So I will warn you now, I will warn you again, and it's in big red letters in the assignment. But I think I have yet, since I made this assignment, I have yet to have a semester where somebody doesn't turn it in with either a set or an array or something like that. And it's like, you don't need that. You actually make it more complex if you do that. This program, Java or C++, or even Python, should be about 30 lines if you use integers. If you use anything else, it's going to be closer to 100 to 125 lines. So if you use a set or an array or anything like that. So bit strings are used. And here all we're doing is we're saying, I've got a set. Actually, I'll try and do it on another slide. A bit string is just a string of bits. In this case, what we do is we use the bits in there to indicate that something either is or is not in a particular set. There are lots of things in computer science where we do this sort of concept. So let me get to that before I show you an example of how we might do it. First of all, this program is not Prolog. I will be emphasizing that as well. I've had people ask me questions many years. Oh, so how do we do this in Prolog again? And no, you can do it in Python. This is not a logic problem. This is a set manipulation problem. It's a string of bits. We use the bits to indicate the smallest memory value. I know most of you have not had 2810 yet, but one of the things that is commonly done there is to look at bits within values. For example, you will be given a string of bits like this, where in the old FAT file system, the date was indicated by a string of bits. 16 bits was used to indicate the date. So I always needed 32 bits, or 32 bits. I always needed 5 bits to indicate the day of the month. Why is that? How many different days can there be in a month? 31. So how many bits do I need to represent 31 different values? 5. 2 to the 5th is 32. 2 to the 4th, if I only have 4 bits, I can only represent 16 values. So I need to represent at least 31, so I have to go to 5, and that's what we do. We take 5, and we actually write the binary representation of the date. So if it's the first day of the month, I'd have a 1 here, and the rest would be zeros. And we just count positive values. When they're all 1s, that means it's the 31st, and that's happy, happy, joy, joy, or whatever expression you want from cartoons or something like that. This is an exact number for the day of the month. My month, I've got 1, 2, 3, 4. Why do I have 4? How many months are there? 12. So if I had 3 bits, how many different values could I represent? 8. If I have 4 bits, I can represent 16. So I have to have enough bits to represent all the possible values. Since I've got 12 months, I need 4 bits to represent any of the 12 months. So that's how we do that. When Microsoft did this in the early 1980s, at that time, computers were 16-bit computers, woohoo. It was twice as big as the 8-bit computers that we had in the 1970s. So everybody was happy, and they said, oh, we're just gonna take these 7 bits and we're gonna add it to get the year. So the world began when Microsoft did this. So the first year was 1980. And what that number is how many years past 1980 you are. So what you would do is you would select these bits and figure out what number that is. Actually, normally what you do, when you're in 2810, what you'll do is you will get a number, a 16-bit value with a 1, a 1, a 1, a 1, 1, 1, 1, and then all zeros. You will AND them together and then shift it over 9 places so that it is at that point an integer number between 0 and 127, and you will add it to 1980 to come up with the year. So when you take 2810, you'll do that in assembly language. Everybody's favorite thing in the world. So here we're going to be looking at bits in that way, but we're going to be doing it in a higher level language. But we need to be able to store the values and retrieve them. I have another example here, another one from 2810. You get more opportunities to do this than you can imagine. In MP3 files, there's a header frame, or a header at the beginning of a frame. That frame header contains information on how to decode a section of the song that you listen to. Part of that is how many bits per second it was recorded at. If you have the wrong number, then it doesn't sound right when you try and listen to it. So this is the way that it's taken care of. What we do is we have a 32-bit number here. The first 11, 12, 17, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 15 bits are all A's, and they're supposed to be, or not 15, 11 bits. The first 11 bits are all 1s. That tells the computer that's trying to decode this is a frame header. So as you're streaming over the internet from Spotify and it sees those 11 bits, it says, here's going to be the decode information for the music you're listening to. And then I've got a version, a layer. I don't remember what the D is. I don't remember. And then I've got 4 bits that tell me the row in the bit rate table. There's a table that's used. So what you do is you combine these 2 bits with those 4 bits, and you get a location in a 2-dimensional array to say that's the bit rate value, so you can decode the music and listen to it the way it's supposed to be listened to. So we use bits all the time. Anybody in here ever use the internet? Version, layer, and the bit rate for recording. Anybody use the internet in here? What's the most common protocol to go over the internet? Begins with a T. TCP/IP. Transport Control Protocol and Internet Protocol. And this is just an example of it. The TCP header is 32-bit row. So I have a source port, destination port, each 16 bits, 32-bit sequence number, acknowledgement number, data offset, a reserve, which has actually never been used. And then I have 1-bit values here that indicate what kind of communication I have. So the entire communication process between 2 ends is started and finished by using these. You send an ACK, they send a SYN ACK, you send a SYN-ACK back, and then you can communicate, and then when you're done, you send a fin, which is the finish. SYN is synchronized. ACK is acknowledge, or pardon me, you send a SYN at first. I want to synchronize with you. Hello. I want to synchronize. They acknowledge you're synchronized and send you a synchronize and say, I got it. Here's my synchronization information too. You send that back and said, I got yours, and this is what I got. And then you say, oh yeah, we can communicate now. So those bits are what controls that entire process of starting a network connection using TCP/IP. Operating systems, anybody in here ever use a hard disk or a solid state disk? Solid states are actually a little different, but hard disk, anybody still have, you guys still have mechanical disks? Yeah, most people do. If you've got anything bigger than like 1 terabyte, or it's probably going to be mechanical. The table that's used to tell what portion of the disk is in use is bits. Because using integers, rather than 1 bit per block of data, I'm now using 32 bits. A big waste of space. Rather than losing like a couple of 100 megabytes when you format your drive, you'd be using like a gigabyte or more. Or actually several gigabytes for all of the data you have to keep about what's allocated, the file system structure of directories and stuff like that. All has to go on the hard drive as well. All right. So the idea behind bit streams is we save space. We access the bits using logical operations, actually bitwise logical operations. And they happen to be the same in C, C++, Java, Python, Ruby, Perl, and almost any other language that I've ever seen. The logical operators and their bitwise equivalents are pretty much identical between all of them. We have and, or, not, XOR are their operators. Because we're operating at a bit level, usually it's implemented in the machine. So I can do it really, 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 really fast. Not important to you to think about right now when you take 2810. You'll be talking about doing things fast because that's one of our key goals when we design hardware, design a CPU. As an example of decoding, in this particular case, I don't remember even what I had. This looks like January 12th of, let's see, 2/16, not 64, 32. Wait, no. Yeah, that's 16. So 32, 8, and 2. So 42 plus 80 would be 2022, January 12th of 2022. And that's what we should have had there. Oh. Yeah, when I made this, I actually intended to go through and say, okay, yeah, this is 32, or this is 42, or not, yeah. 42, this is 1, and this is 12. So this would be January 12 of 2022. We could do today as well. That would be 43, so it'd be 0, 1, 0, 1, 0, 1, 1. Today's the 9th, so 1, 0, 0, 1, and it's the 12th. So we'd have the same number there. So I know some of you were alive 22 years ago. I was actually, my job was at the Pentagon, but I was out of the country. So otherwise I would have been under a mountain in an unnamed state, playing cards with Dick Cheney for the next 2 weeks. I was supposed to be the first person out of my office to go, and I was out of the country, so I couldn't. Came back 12 days later and looked at my building, and one whole place, part of it, was collapsed. All right, homework 3, bit representation of sets. We're going to be using Java, Python, C++, C. If you want to use another language, talk to me first, please. I did have somebody write a Rust program once. I felt like shooting myself when I looked at it. But, you know, it's one of those things. Do not try to use Prolog. Prolog will not work well with this. So, but let me give you an example of what we're talking about here. So let's say, for example, that I have, yeah, we'll use fruit. We have a set fruit. And our set contains the items apple, banana, kiwi, cantaloupe, watermelon. These are in no particular order, as you know. Lemon, lime, orange. 1, 2, 3, 4, 5, 6, 7, 8. Orange, peach, 9, and let's say rambutan. Very nice fruit. I don't know if you've ever had it. You got to be careful of the pits. It's got to, but very sweet when it's ripe. I would not recommend buying them here. They look black. That means that they have aged quite a bit since they were picked. They should be reddish, maybe the ends red, but the ends of the little, they look like little furry caterpillars. So, but though that's our fruit. So what we could do just add them to an array. 2. But to do that, how would I have to store these? How can I represent apple in an array?
You'd have to make, you want us to use integers, right? You'd have to.
No, I'm just saying, how can I represent apple? Probably have to use a, begins with an S, ends with a string, yes, a string. And what I'd have to do is I'd have to make an array of strings and say, okay, what do you have in, what kind of fruit do you have? And they'd say, well, I have an apple. But I'd have to allocate memory in my computer for a string. I don't know how big it is. Is it a watermelon? Is it an apple or something else? Every string in my array would have to be big enough to hold that. We normally don't think of it because normally we have a lot of room. But what if I'm putting this inside a thermostat or inside a refrigerator? So I may have a list of things, but I don't want my array to take up a lot of space for those strings. I want exactly the right size. And so we have, when you get to the other thing that you'll have in your assembler class is, as you're writing out the date, you have to be able to store the name of the month into memory and be able to get to it using the number that you get. Well, we'll use that same idea here. So rather than using an array, which will get you 0 credit, well, not 0, you'll get roughly half the credit, instead, or use an index into an array of names for fruit. If I only have fruit that belongs to one person, that's fine, or one store, let's say. But let's say that I'm running every Smith's grocery, and I need to keep track of what they have in their inventory. So I can have one list of the different names of fruit, and then I can use a bit string to say, okay, store number 327 has this one, this one, this one, this one, this one, and I'm only using that many bits in order to represent it. So I don't have to save strings for each one of the stores. I can just use bits to indicate these are all the fruits that we carry. This store has these, this store has these other ones, this other store has these other ones. I can save a huge amount of space by doing that. So what we would have is, let me change colors here and check the time. So this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Amazingly, that just happens to coincide with the numbers that we're going to be using in the set, the sets that we're going to be dealing with. But here, what I could then say is store number, I said 320, let's just say 56. No, 42, because it's the meaning of life, the universe, and everything. Store number 42 has, well, which fruits does it have? What fruit do we want at this store? Give me some fruits. Everybody has bananas. Why do I put it there?
Because if you put it in the first one, it would have been an apple, right?
Yeah. This is in normal numeric bit position. For integers. They're also the power of 2 that bit represents if I have an integer value. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I had 32 possible fruits, or let's say 64 possible fruits at every single store, all I'd need is a 64-bit integer, and I could set the bits for whatever fruit happens to be at that store. You know, blueberries, strawberries, bananas, plantains, star fruit, dragon fruit, whatever. I don't think I've ever been in a store that had more than 64 fruits. So we'll do essentially the same thing. I have bananas. What else might I have? Lemons, 5. Anything else? Let's say we want some oranges. We're almost out of season. Most people would like peaches while they still have them, and maybe some watermelon while they're still there. I haven't seen well, no, cantaloupe is still out, but not too much. So let's say that's what I have. So this store, all I would have to do is check to see which bit is set to say, oh, bit 1 is set, so banana. Bit 4 is set, so watermelon. Bit 5 is set, so lemon. Bit 6 is not set, so no limes. I have oranges, and I have peaches, and no rambutan. That's too bad. But that's really the idea that we're going to do. So each bit position, this represents 2 to the 0th, 2 to the 1st, 2 squared, 2 cubed. In binary numbering, that's what we do. In base 10, it would be 10 to the 0th, 10 to the 1st. So we've used positional notation pretty much our entire life. We have I'm trying to remember which country it was. I think it was modern day Iraq where they came up with the Arabic numbering system, but I'm not sure. But we called them Arabic numerals because they were in use in the Arabic world. And in the, I don't remember when they were actually adopted in Europe. I think it was around 700 or 800 AD. Because before that, what did we use? let's see, to this year is, and I was informed by somebody that it doesn't have to be this neat and go in this order. That's our current year. Very meaningful. Harder to manipulate. How do I subtract 50 from it? Come on. There. That'll be easy. MMXXIII minus L. And you wonder why, actually it's kind of amazing that their engineering was as good as it was when they couldn't do math very easily. But yeah, we owe a debt of thanks to whoever invented the positional numbering system, the powers of numbers and things like that, because we've dealt with hundreds and thousands and stuff like that for a long time. It's just that for whatever reason, we didn't use a symbology that said, well, why don't we just use the position of the digit to indicate what it is, and then we can have the digits 0 through 9. You know, there's 0 of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 would be the next position. So that's our numbering system. That's what we're going to do. So what we'll end up doing, and we have this in the, get my mouse to the right place. We have this in the assignment. Let me be a good professor here and pull it up for you. If we come down here, that's Boolean algebra. We're in what, week 3. I strongly recommend, well, let me open both of these. First, doing the homework, because what you need to do is spelled out almost perfectly in here, but not quite. So I tried to get as close as I could. So, but what you'll see here is I talk about the bitwise operators. Bitwise AND as opposed to logical AND. Logical AND returns a 0 or 1. Bitwise AND looks at your 32-bit integer and checks each bit against the corresponding bit. And if it's an AND, if both of them are 1, the result will have a 1. If either one is a 0, you'll have a 0. And what you end up with, you have 2 integers to start with, you have an integer to end with. With logical operators, I have one thing and I AND it with something else, I'm going to get either a 0 or a 1, not any other integer value. And that's the difference between them. A regular AND would have 2 ampersands. Bitwise, a logical AND would have 2 of them. Bitwise only has 1. Same thing with OR. Bitwise OR is a single vertical line. There are other bitwise operators that are in the other assignment, but this is the homework. What I really wanted to show you here was, this is a function, and you can do this. This one is actually plug and play. Well, actually, no, I've changed the output lines. Other than that, this will work in Java. It will work in Python. It will work in C++. It will work in C. Other than the printing, this will work in any one of the languages we program in. You just have to declare I as an integer at the beginning. This is an integer value. What this is saying is, take the value, shift it over to the right by that amount, and it with 1. That means if I have, let's say, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, something like that. And let's say that this is the value. This is I. What do you want I to be? 4. It says shift it over by 4, and then 1 is always going to equal a bunch of zeros with 1 in the last position, because we're talking 2 to the 0. So the integers in the computer are actually stored in their binary representation, always. So 1 will be stored as a binary value of 1. So if we shift this over 4, that means these guys go off that way, and we wind up with a 1, 0, 1, 0, 1, 1, and it fills with zeros. So we shift it over to the right by 4. We now end with 1. So it says, okay, bitwise and. I'm going to erase the 2 to the 0. Bitwise and. 1 and 1 is 1. 0 and 0 is. Anywhere where I have a 0, I'm going to have a 0. So that's my result. Because this bit is set. If it was a 0, I'd get a 0. If it was a 1, I'd get a 1. And all we're trying to do here, this will print the binary representation of an integer. And that's all you have to do is copy and paste this, change the print with a quote to system.out.print, not print line, please, or cout, or whatever. For Python, it would be a print with your termination being just a null string. If you're doing Python, just either print a 1 if it's a 1. So if it's greater than 0, print a 1. If it's not greater than 0, print 0. And do that for all 31 bits. I start at 31, so let's say I've got a number like, let's see, 0, 0, 0, 0, 0, 0, 0, 0. We're not going to go crazy here. So these are the high order 16 bits, so I'm looking at something less than 65,000. Now I'm looking at something less than like 4,000, or 4,096. So 1, 2, 3, 4. We'll do a 1, a 0, 1, 1, 0, 1, 1, 0. So this would be 6, and this would be B, if I'm looking at hex, or 11 times 16. So 160 plus, 11 times 16. So 176 plus 6 would be 182. So this would be 182, and if I shift it over 4, I have a 1, and this would print a 4. So what that function would print is this, exactly. So if I type in a number, it will print the bit representation of that number. That's what this function does. Question? Do this first. I've got 30 seconds. So let's take a quick look at the program here. Oh, that's the quiz. Why did I open the quiz? Hello, we're almost out. Almost. Program. Manipulating bits. Note that it's called manipulating bits, not called sets. So that's the other reason why I'm trying to keep you from writing it using integers. Written in Java, I need to put, oh, there's Python. Python's in there. Bit string, it's just saying bit strings. We're going to use the digits 0 through 9. So we could use a 16-bit integer. We'll use, for all my examples, I use 16 bits because 32 bits becomes all of these are zeros. Most of these are zeros, and then I've only got the last 10 bits that would have anything in them. So rather than write all 32, I just write the last 16 for all of my examples. What we do is we add things. One of the biggest things to do, okay, you must use integers, is to look at this document and it talks through the whole idea here. So we're going to use integers. Once again, I only have least significant 16 bits. It's actually 32 bits, but it doesn't really matter. If I shift 1 by 0, I get a 1. If I shift it by 1, it moves over. So I'm shifting this by this amount, and it's going this direction because that's the way they're pointing. If I want to shift the other way, which is what happens in the function where I print it, it's shifting the value to the right. So this is what the bit representation ends up being. To add something to my set, I would need to ask somebody, please enter the element for the set. And then once they enter it, I can store it into a variable. For example, I could store it into value. Please enter the next element of the set. Store it into value, check, is it less than 0? Is it greater than 9? If it is, it's not a valid value for our set. Otherwise, I shift 1 over by that amount, and then I do a bitwise AND with whatever's in the set to set it. Or a bitwise OR, pardon me, with whatever's in the set to set it to a 1. If I want to check that bit, I'd do a bitwise AND. And the result would tell me, was it a 1 or not? So I can check to see, is it greater than 0 or not greater than 0? So bitwise OR is used to set the bit, you read in the value, you perform that operation, and bitwise OR it with the set. So that would be, now let me get to my slides. Sorry, I'm going to keep you about another minute or so. So here, prompt for the set element. Read it in. And I'll just, for example, save to value or some other variable. Then I'd check if value is less than 0 or value is greater than 9, print invalid element. Else, and you'll note this is kind of pseudocode, I'm not doing it exactly. Then, let's see, well first I'd declare integer vset, and we'll initialize it to 0. Otherwise, and this would be while, well actually the other thing that we do is prompt for number of elements while elements is greater than 0, prompt for the set of elements, or prompt for the set element, and then if it's good, we just say vset or equal 1 shifted left by value. And then I'd have my element minus minus, and that would be the end of my while. So this would be, how do I read in this set? First of all, ask, how many elements are in the set? 5, 9, whatever. I can check to see if it's valid or not. You can do that if you want. It's not a requirement. I don't think. It may be in the. If it is, it's in the assignment. Just read it in, and then while that element number is greater than 0, ask for a value. a value in the set, an element in the set. If it's valid, if it's not valid, ignore it. If it is valid, set that bit. So you might say, well, what happens if they enter 3 times? Well, that means 3 is in the set. Don't worry about checking for duplicates or anything else. Remember, everything in the set is unique. For printing, I just have a loop that goes from 0 to 1. I do another while loop, and I use my loop control variable. I'll shift 1, 0. If it's a 1, I print that element 0 is in my set. If I is 1, and I shift, and I do the and it's not 0, then I say element 1 is in my set, and I just loop that way to print out which elements are in the set. I print out the looped variable, I. 0's in the set, 5's in the set, 7's in the set. That would mean if I shift 1 by 0, and I do an and it's non-0, that would mean 0 is in my set. So we'll have time to talk about this on Thursday as well. In room 318. So this floor, this is down the hall. It's where we were supposed to be for the semester. But Dr. Valle needs some of the computers in this room because they don't have any in that room. And we're going to be kind to your fellow students and let them use the computers in this classroom since we don't really need them too much. So that's where we're headed with the programming assignment. We'll talk about sets more next time and any questions you may have on this or the homework. I'd recommend giving the homework a try. It's kind of fun to go in and type in a number and say, oh, that's the bit representation for negative 255. And you can actually see all of them. All right, guys, have a good one. Sorry for keeping you an extra 8 minutes. Oh my goodness.
Thank you. Thank you.
You're welcome. See you later.
Quick question for you.
Mm-hmm.
So we talked about